Hello, physics, again, one more time. So I went through quite a bit of information, and it was interesting, exciting, important, and none of it was recorded. So, boy, a little frustrating, but hey, I'll rally here. Just like you guys need to rally here. Anyway, I do want everybody 2 notebooks now. 2 notebooks, just like Bio 1, if you had me in Bio 1. Meticulous notes. You're going to be showing those to me, or probably, well, you're definitely going to be showing them to me eventually, but you're going to be taking pictures in a timely fashion. I'll set up the time that I want double notes. Now, you don't have to redo calculations twice. No. But anything on theory needs to be recopied. Calculations just need to be done once. And you need to hand write these. I need to know that you're taking these notes. Don't mess with me. I'm a wild card these days. So do it yourself. And again, one more time, take advantage of this time to pursue your intellectual endeavors. And I'm going to help you do that, whether you like it or not. All right. So anyway, this is where we got cut off. Notice this is the universe here. And here's the Milky Way galaxy. So we are one galaxy with many billions of stars. Notice our planet, this would be our sun, in which the planets would be in orbit around. Notice our sun is out in the suburbs. So here's Grand Central Station here, and we have to move out to the suburbs where it's a little bit more quiet, a little bit safer here. So this again is one galaxy, and then of course the universe is quite a bit larger. It's really tough to get a grasp on just how much space there is in space. It really is. Let's go to the next. Let's go to the next picture. So notice, here's the Milky Way galaxy, and of course we're going to be off here in the suburbs somewhere. It's the distances, the vast differences between object and space are just very difficult to comprehend. So a light year is not a time, a light year is a distance. It's the distance that it takes for light to travel 1 year. So let's stop and let's think about this for a moment. Light is traveling at about 3.00 times 10 to the 8th meters per second. So in a blink of an eye, light is going to travel around the world several times. If we wanted to convert that number into miles per second, it'd be approximately 186,000 miles per 1 second. So consider the distance traveled for 1 year if light is running the race. It's amazing. Now, if you're in the Milky Way galaxy, our closest star is at least several light years away, so that's within the Milky Way galaxy. If you want to compare distances from not within the Milky Way galaxy, the closest sun to us, so there you're talking, I believe it's 5 light years to that nearest star. But notice if we want to go to other galaxies, the distances go into the many, many, many light years. So here's a couple, a famous neighboring galaxy. Here's the Milky Way. So this is the Andromeda galaxy. Notice this gallery has a is going to have a huge number of bright, shining suns, same as here, same as the Milky Way galaxy. So keep that idea of this vast amount of distance between what are the nearest neighbors of our galaxy. Now this image here is truly amazing. This image was captured by the Hubble Space Telescope, which is orbiting the Earth. And do yourself a favor, and if you Google Hubble Space Telescope pictures, there's a huge number of pictures of different structures, nebula, distant galaxies, spiral galaxies, the Horseshoe Nebula. You can take Hubble has taken pictures of literally galaxies in formation, the birth of galaxies. So it's truly amazing. It's worth your time to look at that. These are your tax dollars at work, in terms of your parents' tax dollars at work, in terms of this is a federally funded project, and it's really cool. Anyway, getting back to this picture, notice these are not individual stars. These are separate galaxies. All of these are galaxies, and they all have many millions and billions of stars present. Truly amazing. This is deep space photography. So essentially, what you're looking at, if you were to hold up a penny away from your arm, looking up directly ahead at the sky, and then you take that penny and you maybe go about 1% of that penny in terms of the diameter, and you went deep into space to take a picture, this is what you'll see. So this takes up just a tiny, tiny fraction of what you can see of the just with the naked eye of the universe. And notice how abundant. And again, these are galaxies here. So this is really one of my all-time favorite pictures, just because it shows you you really get a good idea of the immensity of the universe, and also the abundance of visible matter that's in the universe. Well, I just couldn't resist. This is Hubble Deep Space Deep Field Photography. That's with ultraviolet light enhancement, and these are all galaxies. And this is deep, deep, deep at the corners of the universe. Spectacular. The distances between these objects is truly tremendous. So we have, that's a nebulae. Huge amounts of gas, many, many, many stars. This is a Hubble famous picture. This is the birthplace of many, many suns, and probably the birthplace of a galaxy. It's a violent universe. There's explosions. This is a photograph taken with a special camera, and this is showing the microwave background radiation which permeates the entire universe. This is essentially hot, medium, and cold spots throughout the universe. This is kind of like a temperature grid of a huge amount of space. Now, when we're talking about temperatures in space, when I say hot, I don't mean room temperature. Hot in space is going to be 1 to 3 Kelvin in the temperature. 1 to 3 Kelvin, probably more close to 3, with slight micro variations going above and below 3 Kelvin. What is 3 Kelvin? That's going to be negative 270 degrees Celsius, and that's about negative 450 something Fahrenheit. Why is this important? Because these slight variations in temperature in deep space represent the leftover energy that was produced by the formation of the universe, and that's the Big Bang. So these changes in temperature, these slight temperature variations, are ripples, so to speak, of the original Big Bang, of which the entire universe was created. If you have an old-fashioned television set, you could plug that sucker in, find a channel that's not broadcasting anything, and all that fuzz, the static that you're looking at, about 3% of that static is this microwave background radiation that's making its way from space to the antenna, and it's giving us little whispers, if you will, whispers of the original formation of the universe, which happened many, many billions of years ago. So, let's move on. Now, when we're studying the universe, I wondered when I was your age, how is it that they determined that the sun was made of hydrogen and helium? Not only we I know, I didn't know then, now it's not just hydrogen and helium, there's other elements as well. There's boron, beryllium. There's small amounts of iron present in our sun. How the heck, excuse my language there, how the heck do they know that? Well, we can do spectroscopic analysis of light as it travels either from a neon sign or from the sun or from distant galaxies. So we can analyze that light. And when we analyze that light, different elements which are part of the composition of that light, so for example, hydrogen, helium, sodium, iron, etc., if different elements are present as a makeup of that particular material, or the sun in this case, then they will leave a specific color, which then can be, let me state it this way, that specific color is going to be passing from these objects, and then we're going to run those different colors through a prism, and then we can analyze the colors produced, and those specific colors will leave a fingerprint, if you will, of themselves. So astronomers, by analyzing light, can dissect the spectrum of the light, which is what's going on here. We got to run that through a spectroscope. And then there's going to be a fingerprint of the different elements that compose the material that's producing the light, like the sun. So we're going to find sodium. We're going to find the fingerprints of potassium. We're going to find lots of hydrogen and helium. That's the main nuclear fuel of the sun itself. So notice we're going to analyze this galaxy here, the light coming from this galaxy, and notice we're going to determine the spectral fingerprints of these different elements. So this idea is important, and at some point I'll be posting a video where we'll take a little closer look at what's going on here. Now you guys know that the electromagnetic spectrum is actually a continuum of different wavelengths of energy that goes from long wavelengths to shorter wavelengths. So what we see, here's visible light, here's red on this side. Notice red has longer wavelengths, and here we're going to get violet on this side. And notice that we're getting shorter, so we're going red has long wavelengths here, violet here. Easy to remember the colors of the spectrum. Roy, G, Biv, so there's blue, red, orange, yellow, green, blue, indigo, and violet. Easy to remember. Red, think of, red's going to have the long wavelengths. So red, long wavelengths. Violets are going to have the short wavelengths. Of course, you can go into the ultraviolet range if you get shorter and shorter there. So we can move here to these short waves and then move off into shorter and shorter and shorter, which would include X-rays, for example. So Roy, G, Biv, red, orange, yellow, green, blue, indigo, and violet. The wavelengths of red are going to be long, so think of a long stem rose, and think of a short stem violet. So we got the long stem red rose, and we have the short stem violets, and then if you know Roy, G, Biv, you can always give a qualitative determination of long, short, and medium. By the way, what are these wavelengths? These wavelengths are measured in nanometers. So this is 1/1,000,000th of a meter in wavelength. So the distance here for red light from wave, and I know you guys have studied waves, the distance here goes from peak to peak. This would be about 700 nanometers if we have red light. 700 billionths of a meter. Violet's moving down to about 400 nanometers. And then, of course, you're transitioning from 700 here to 400 here. Once you get shorter than 400, you're moving into the ultraviolet category. And that ultraviolet category is invisible to the naked eye. Of course, your skin is quite sensitive to ultraviolet light, and so is the back of your eye. The retina of your eye is as well. So be careful out there. This ultraviolet light, you don't see it, but it's hitting your skin, and it's hot. Okay, so I literally wanted to back up and take a look at the entire electromagnetic spectrum, since it was difficult to do it on the overhead with the setup that we have there. So again, look at the relationship between wavelength as you go from the AM band all the way to those high energy gamma rays on the far right. Notice the approximate wavelengths at the bottom. So wavelengths could be as long as 3 football fields, but they could be as short as 3 times the diameter or 30 times the diameter of a hydrogen atom. Boy, that is quite small. Also, look at the low energy side of the wavelength and the high energy side. As you move to the right, you'll go through the visible spectrum, hit those high energy ultraviolet lights, and you're getting higher and higher energy. Look at the frequencies. The frequency are the number of cycles that pass a given point per second. And the frequency is going to be measured in hertz. So visible light, for example, would be maybe somewhere in the range of 1 times 10 to the 15th hertz. That would be 1 times 10 to the 15th cycles that are passing a given point per second. You need to understand the relationship between frequency, wavelength, and energy content. All right, so my arms were getting tired, so I had to back up and use a little stability here. Again, you need to understand the relationship between wavelength, energy content, and frequency. So let's start with wavelength. Long wavelengths on the left, short wavelengths on the right. Notice, as the wavelength gets shorter and shorter and shorter, notice the frequency of those waves goes up and up and up. So if you move over to, let's go with ultraviolet light, maybe the frequency is 1 times 10 to the 16th hertz, or cycles per second. What does that mean? The number of cycles per second are the number of wave peaks that go past a given point per second. So that's frequency. What about energy content? Energy content and frequency, they go hand in hand. There's a direct relationship. As you move from left to right, from radio waves all the way through X-rays, what you're going to see is that the energy content is going to get higher and higher and higher. Now notice the X-rays. Maybe you don't think of X-rays as dangerous, but they are. If you were taking X-rays every day for a year, it would be very, very dangerous. The people that work with X-rays every day, for example, the dental technicians, for example, or the hygienist who's ever taking your cavity X-ray picture so that the dentist can analyze that, they head for the hills when they are taking those X-ray pictures. They get the heck out of Dodge because they cannot be exposed to those X-rays over the long term. Of course, don't worry. Health effects are negligible if you're having a small number of X-rays per year. All right. Well, so this is an important part of the accelerating universe that I want you to know. So we're kind of adding different aspects of physics to the video, the accelerating universe. I'm not sure how much of this you've had, but if you have had it, I want you to relearn it. Final exam is coming up. Also, we are going to discuss quantitative aspects of this, which are going to be on a different video. So, what I want to do now is go back to the accelerating universe.